Welcome to the summary of Chapter 2, which is Statistical Learning. Statistical learning involves the use of data to understand underlying patterns and make predictions. It encompasses a variety of methods and models aimed at analyzing and interpreting data. We learned some key concepts that are involved in the statistical learning, of which is predictive modeling and regression and classification. For predictive modeling, creating models to predict outcomes based on input, which one of the examples we learned in this chapter was the prediction of sales based on advertising budget for TV, radio, and newspaper. For regression and classification, we have two main problems which they are involved in predicting a continuous outcome, which is going to be a regression, while the other type of a problem it involves the categorical outcomes, which is going to be which most of the time we deal with it using the classification. We also learned linear regression, which is a fundamental method for understanding the relationship between dependent and independent variable. Independent variable can be either one or more than one. The famous formula for linear regression is y equals to beta naught plus beta 1 times x1 plus beta 2 times x2 plus and so on up until beta n times xn, plus we add the epsilon, which in this scenario represents the error. We have also touched on bias variance trade-off, which is crucial in selecting models that generalize well to new data. It involves the bias, variance, and the trade-off, which means the bias is the error due to overly simplistic models, variance error due to overly complex models that fit the training data too closely, and the trade-off is finding a balance between bias and variance to minimize overall prediction error. We learned also about the model flexibility, which involves the overfitting and underfitting in this scenario. Then for overfitting, overfitting basically models fit the training data too well, capture noise and leading to poor generalization, whereas the underfitting, we can explain it this way to say model is too simple to capture the underlying structure, leading to poor performance of both training and test data. So there are some methods as well that we learned to so that we can be able to mitigate this problem, where we looked at the cross-validation regularization. So for the cross-validation, split the data into training validation set to ensure the model generalize well. Generalization, adding a penalty to the model complexity. There are other problems that we also learned about, which is the classification problem. So for classification problem, classification involves assigning categories to new observation based on training data. So in this scenario, we looked at the k-nearest neighborhood and some couple of models, which is decision tree, support vector machine. Then by the k-nearest neighborhood, it is a simple non-parametric method for classification and regression. The decision tree, a flexible interpretable model that makes decision based on a series of binary split in the data. Then lastly, when we look at the support vector machine, which is a powerful method for classifying, particularly effective in high dimensional space. So the idea behind the k-nearest neighborhood is predicting the outcome based on the k nearest data point in the feature space. The decision tree is easy to it has the strengths and the weaknesses, which is easy to interpret, handle both numerical and categorical data, which is the strength part of it. Whereas the weaknesses, it is highly likely to overfit. For the support vector machine, the idea behind that is to find the hyperlane that separates different classes with a maximum margin. Summarizing the overall chapter is that statistical learning encompasses a wide range of methods to analyze data and make predictions. Also, understanding the bias variance trade-off, avoiding overfitting, and selecting the appropriate model complexity are crucial for building effective models. The techniques like cross-validation, regularization, and ensemble method enhance model performance and generalization. Thank you.